Dozens of warships are bombarding your position. Shells rain down like a storm. After the shelling stops, the enemy begins to land. You immediately call for reinforcements, but the telephone line has been destroyed by the shelling. With no other option, you order the runner to call for backup. Until then, you must hold off the enemy. As the ramps of the landing craft drop, you open fire on the enemy. The enemy suffers heavy casualties, but the enemy forces are overwhelmed. You have no choice but to keep shooting. As you continue to fire, the water in the cooling jacket keeps heating up, and the pressure continues to rise. The high-pressure steam escapes through the exhaust pipe at the top of the cooling jacket, flows into the rubber hose, and finally enters the cooling water tank at the bottom. There, it is cooled again. Just as you're firing, the shell lands beside you. Fortunately, you are not seriously hurt. You plan to change positions, but you can't lift the heavy machine gun alone. You have no choice but to stay and keep firing. Unexpectedly, the cooling tank is punctured by shrapnel. You remain unaware. You keep suppressing the enemy with continuous fire, but under your sustained fire, the water in the cooling jacket quickly evaporates below the barrel level. You must immediately refill the water. You lift the cooling tank only to find very little water inside. It's nowhere near enough to cool the barrel. Suddenly, you spot a cooling tank on a nearby position. You decide to retrieve it, but as soon as you step out of cover, you're forced back by a hail of bullets. Left with no choice, you remove the water jacket from the barrel. You expose the barrel to direct air contact and use the surrounding cold air to cool it. You continue firing at the enemy, but the barrel quickly overheats. That's because standard barrels are thinner, so they have low heat capacity, and their surface area is limited, reducing their ability to dissipate heat. So you switch to a heavy barrel. It stores more heat and has a larger surface area, allowing it to transfer heat to the air more effectively. You immediately replace it with a heavy and open fire again. This time, the barrel doesn't overheat immediately, but after prolonged firing, it still overheats. Looks like you need to increase the barrel's surface area instead, so you switch to a barrel that has many transverse cooling fins. These horizontal grooves greatly increase the surface area of the barrel. You continue shooting at the enemy. The heat from firing passes through the transverse fins and disperses into the air. The overheating rate noticeably slows down, but with your intense rate of fire, the barrel still overheats. That's because the transverse grooves are cut around the barrel to add surface area, but they interrupt heat conduction along the barrel's length, causing local hot spots. You recall that when the machine gun fires, high pressure, high temperature gases rush out of the muzzle, creating a blast wave. This blast wave momentarily clears the air near the muzzle, rapidly lowering the air pressure there. This creates a low-pressure zone, then surrounding cool air rushes in to fill the void left by the outgoing hot gas. However, the transverse grooves encircle the barrel, blocking longitudinal airflow. This reduces convection efficiency, causing local heat to accumulate and not dissipate quickly. So you switch to a new barrel with longitudinal cooling grooves. You fire at the enemy. The heat generated during firing travels along the longitudinal grooves from the inner barrel wall to the outer surface. Thanks to the groove design, it better increases the surface area along the barrel's axis for heat dissipation, helping heat escape quickly. At the same time, the longitudinal grooves allow cool air to flow smoothly between the channels, quickly carrying away the heat from the barrel. Now the machine gun overheats much more slowly, but because of the overwhelming number of enemies under your intense, sustained fire, the barrel still overheats. Now what should you do? You realize that the airflow around the barrel isn't fast enough. If you could speed up the airflow, you can improve cooling efficiency. So you add to the outside of the barrel a perforated shroud. The front of the shroud is aligned with the muzzle. You then open fire on the enemy. During firing, the muzzle blast creates a jet effect, and the holes in the shroud allow cool air to rush in quickly and force hot air to be expelled rapidly. This creates a continuous airflow cycle, which speeds up air movement around the barrel. Now the machine gun can fire for longer periods, but under continued firing, the barrel still overheats. So what now? Is there another way to further increase airflow around the barrel? What if you remove the holes in the shroud and leave the rear of the shroud open? Would that increase the flow speed? You quickly install a new shroud and fire at the enemy. When a machine gun fires, the muzzle blast produces a suction effect that draws air rapidly forward through the shroud. Then new cool air enters the shroud, absorbs the heat from the longitudinal grooves, and is expelled with the next shot in a repeating cycle, effectively cooling the barrel. You time your shots carefully, pouring continuous fire at the enemy. You know that the barrel expands when heated, increasing friction between the bullet and barrel, causing the barrel to overheat faster. In extreme cases, it can jam the bullet and cause a burst barrel. So the barrel material should be low expansion alloy steel. This reduces overheating and prevents bullet jamming. Although these designs help prevent overheating, the endless waves of enemies still cause the machine gun to overheat during prolonged fire. What can you do now? You recall that the inside of the barrel has rifling, which rubs against the bullet's jacket during firing. If you could reduce that friction, you could effectively reduce overheating. So you coat the inside of the barrel with lubricant to reduce friction. Then you look at the cross-section of the rifling and begin to ponder. If you change the trapezoidal rifling to polygonal rifling, wouldn't that further reduce friction? So you install the modified barrel and fire at the enemy. As the bullet travels down the barrel, the combination of lubrication and polygonal rifling greatly reduces friction. This helps prevent the barrel from overheating. Now you can fire for much longer than before. Still, after prolonged firing, the barrel overheats again. You're growing frustrated. Suddenly, you look at the ammunition and think about the propellant inside. It generates a lot of heat during firing. So what if you add a mix of talc, Saracen wax, and paraffin, known as a barrel conditioning agent? Wouldn't that help cool the barrel during firing? So you fire bullets containing the conditioning agent. During firing, the agent vaporizes, forming a lubricating film on the barrel wall. This reduces friction between bullet and barrel. It also reacts chemically with the propellant gases, reducing their thermal energy. It can even absorb heat from the barrel and be expelled from the muzzle. Now you can fire for an exceptionally long time. The enemy can't even raise their heads under your fire. Their assault is delayed. In this brief lull, you recall that darker colors absorb heat, so you paint the gun black. It doesn't help much, but every tiny design tweak adds up to noticeable performance gains. The final, integrated effect is impressive. After regrouping, the enemy launches another assault. You immediately open fire. A hail of bullets flies toward them, but this time, they keep charging and refuse to retreat. Fortunately, your barrel holds up well and doesn't overheat for a long time. You keep firing, suppressing the advancing enemy. But under the extreme rate of fire, the barrel finally overheats. Luckily, you've prepared a spare barrel in advance. You quickly use the barrel handle to remove the overheated barrel, install the new one, and resume firing. But the enemy is too many. You can't hold them back. Just when all hope seems lost, reinforcements arrive. They set up their machine guns and open fire. They quickly mow down the advancing enemy. Then the assault guns fire at the landing craft, destroying them. But enemy warships begin shelling your reinforcements, destroying many assault guns. Fortunately, friendly aircraft arrive just in time, dropping bombs on the enemy fleet, sinking their warships. The enemy's attack is repelled. We have achieved a great victory.